Welcome back to the deep dive. Today we're staring into the abyss of something that I think every single person listening has felt just deep in their bones at some point. Decision paralysis.
Oh yeah, it is the universal human condition, truly.
It really is. I mean, if you think about it, it usually starts small. You're standing there in the grocery aisle and you're looking at, I don't know, 30 different types of pasta sauce.
Right, the paradox of choice.
Exactly. Do you want the garlic and herb,
Yeah.
the marinara? Do you go for the spicy arrabbiata? And you freeze. Your brain just halts.
Because you're overwhelmed by variables, cost, flavor, brand, organic versus non-organic.
Yeah, exactly. But then it scales up, right? It's not just pasta sauce. It's those massive life questions like, where do I invest my life savings? Or which route do I take to work to avoid that traffic jam I think might be building up? Or should I take that new job in a completely different city? We are constantly, every minute, processing information, weighing the odds, trying to predict the future. And usually, let's be honest, just kind of hoping for the best.
Yeah, we rely heavily on heuristics, mental shortcuts,
Yeah.
gut feelings.
Right. But here is the hook for today's deep dive. We do this with a gut feeling because the stakes usually are personal. If I buy the wrong pasta sauce, my dinner is mediocre. But how do machines do it? How do algorithms make these choices when the stakes aren't just a bad meal, but, well, how do I avoid a mid-air collision between two commercial aircraft with hundreds of passengers? Or how does a rover land autonomously on Mars when the signal takes 20 minutes to reach Earth? You can't just, flip a coin.
No, you certainly cannot. Hoping for the best is definitely not an engineering strategy. You need a highly rigorous mathematical framework to even begin to solve those problems.
And that is exactly what we have sitting in front of us today. We are diving into a massive, and I mean massive, stack of research centered around the book Algorithms for Decision Making. It's written by Mykel J, Tim Wheeler, and Kyle Ray. And let me tell you, I spent the last week practically living with this book, and calling it a textbook feels like a massive undersell. It feels more like a comprehensive Bible for quantifying uncertainty.
It really is an incredible piece of work. It's a comprehensive guide to the field. And what stands out about this particular source material is that it doesn't just give you the code or the equations, it gives you the underlying philosophy of rationality.
Rationality, yeah, that's a loaded word, isn't it? I feel like when people say in normal conversation, just be rational, they usually mean stop having emotions.
Right, yeah. It gets conflated with being cold or robotic. But in this context, in the rigorous field of decision theory, we aren't talking about being smart in a conversational sense or suppressing your emotions. We are talking about mathematically optimizing outcomes. It's about defining exactly what you believe about the world, which we call your probabilities, and defining exactly what you want your utility, and then calculating the absolute best possible move to bridge the gap between those two things.
So our mission today for everyone listening is to decode the five-part framework laid out in this source material. We're going to take you on a journey from basic probability, essentially, how to make a mathematically better bet than a coin flip, all the way up to multi-agent swarms of robots coordinating with each other in the dark.
It's quite a journey.
Right.
And it really, in a lot of ways, mirrors the history and evolution of artificial intelligence itself.
It does. It really does. And before we get into the heavy math, which I promise you we are going to make painless and actually kind of fun today, we need to define the basic foundational unit of this book, the agent.
Right. So in this literature, whenever we say agent, we just mean the entity making the decision. It could be a physical robot, a piece of software trading stocks, a self-driving car, or even a mathematical model of a human being navigating a store.
And this agent operates in a loop. The book calls it the agent environment loop. I want to really unpack this right away because it sounds simple on the surface, but it's the engine of everything, literally everything we're going to talk about today.
It is the fundamental cycle of existence for these systems. It goes exactly like this. First, the agent receives an observation. It sees something or measures something. Based on that observation, it chooses an action. That action then changes the environment. And because the environment just changed, the agent receives a new observation. And the cycle repeats forever. Observation, action, environment change.
Okay, let's make this super concrete for the listener. Let's say I'm a Mars rover.
Okay, you're on Mars, red dirt everywhere.
Right. My observation is I see a rock outcropping 5 meters in front of me.
Ugh.
So my action is drive to the rock and drill into it.
Right. Now here's where the loop actually closes. Your action physically changes the environment. You have now drilled a hole in that rock. Maybe you dulled your titanium drill bit slightly. Maybe you kicked up a dust cloud. The world is physically measurably different because you acted on it.
And my next observation reflects that new reality. I see a hole, or my camera is covered in dust.
Exactly. And based on that new observation, you decide your next action. Run the spectrometer on the dust. It's a continuous, unbreakable feedback loop.
Simple enough. I see thing, I do thing. Thing changes. But the book throws a massive wrench in the gears almost immediately. It introduces what I'm calling the four horsemen of uncertainty.
That is a very dramatic way to put it, but honestly, it's incredibly accurate because that simple loop I just described, that's the pristine, ideal laboratory scenario. In the real world, things break. Things are messy.
Because nothing is ever that simple. The authors structure the entire core of the book around these four distinct challenges. I want to walk through these slowly because they really set the stage for why this math is so mind-bendingly hard.
Let's do it.
First up, the first horseman. Outcome uncertainty.
This is the slippery slope of reality. You choose an action, but you just do not get the result you expected or asked for. You tell a Mars rover, move forward 1 meter, but the wheels hit a patch of loose sand, they slip, and the rover actually slides sideways 0.5 meter.
So the action itself doesn't guarantee the outcome. The command doesn't equal reality.
Correct. The mechanics of the world are stochastic. That's a fancy word for random. You can never be 100% sure of what a physical action will actually achieve.
Okay, that makes sense. Second horseman. Model uncertainty.
This is a scary one for any system. This is where you don't even know the rules of the game you're playing. Imagine you've been dropped into a giant maze, but you don't have a map. And worse, you don't even know how gravity works in this universe. You literally have to figure out the physics of the world while you are actively trying to survive in it.
Honestly, that sounds exactly like my 20s.
It sounds like everyone's 20s, honestly. You're just pulling levers to see what happens.
Exactly. Okay, third one. State uncertainty.
This is often called the fog of war. In this scenario, you have a map and you actually know the rules of the world perfectly, but you don't know where you are on the map. Your sensors are foggy. Your GPS module is broken. You are flying blind in a familiar world.
And the fourth and final horseman.
Interaction uncertainty. This is the big one. You aren't alone. There are other agents out there in the environment and they are making their own decisions, observing their own loops.
And they might be actively trying to mess with you, like an adversary.
They might be. Or they might just be totally incompetent. Or they might be trying to help you, but your communication link is down so you can't hear them. Other minds, other agents, introduce the ultimate form of chaos into any system.
All right. That is the roadmap for our deep dive today. We have 4 distinct nightmares to solve. Let's start at the very foundation. Part 1 of the source material. Probabilistic reasoning.
This is the bedrock. Because before you can even think about acting, you have to understand what is actually likely to happen. You need a language for the unknown.
And the book actually goes way, way back for the history on this, which I loved. I was honestly surprised to see Homer's Iliad referenced in a dense textbook about modern algorithms.
Yes, the ancient concept of automata. The Greeks were imagining these automatic machines like self-moving tripods serving dinner to the gods at Mount Olympus as early as 800 BC. The human dream of autonomous agents is ancient.
They were dreaming of robots thousands of years before they even had a concept of electricity.
Exactly. And then the book jumps forward to the 17th century to philosophical figures like Leibniz. He had this incredibly beautiful, almost utopian idea that logic could solve human conflict. He basically said that if we had a disagreement, we shouldn't argue or fight. We should sit down together with a pen and paper and just say calculimus, which means let us calculate.
The idea that there's an objective mathematical truth to the question of what should we do.
Right. And to actually do that calculating, we need a way to mathematically represent the real world. And the authors argue, quite convincingly, that we represent the world through probability distributions.
Because in the real world, very few things are 100% certain. You don't look at the sky and say, it will absolutely rain today. You say there is a 60% chance of rain based on the clouds.
Exactly. We call this a degree of belief. We don't have absolute facts, we have sliding scales of confidence.
One of the core fundamental tools the authors use to map this out is called a Bayesian network.
Yes. This is absolutely crucial for understanding how modern machines think and reason about uncertainty.
I really love the example they use here in the book. It's the satellite monitoring problem. Let's walk through this step by step for the listener, because it really finally clicked for me on how algorithmic inference actually works.
It's a classic problem in the field. So imagine you are sitting at ground control in Houston. You are responsible for monitoring a multi-billion-dollar satellite in orbit.
Right.
You can't see it. You can't touch it. You can only look at the telemetry data on your computer screen.
Okay, I'm picturing it. I'm looking at the data feed, drinking bad coffee.
Right. And suddenly the screen just goes black. You have a communication loss. That is your observation. That's the only hard fact you have.
Panic time. Millions of dollars might be gone.
Well, before you panic, you have to diagnose it. In a Bayesian network, you map out all the possible causes logically. What could possibly cause a communication loss? Maybe it's a battery failure, maybe a massive solar flare just hit, maybe the antenna got hit by a micrometeorite and is misaligned.
So in my head, or on my whiteboard, I have these bubbles, battery, solar flare, antenna, and they all have arrows pointing down to the main bubble, which is communication loss.
Exactly. That is the network structure. Now, you have to do the math. You have to do inference. You have to work backward from the symptom to the cause. You ask the algorithm, given that I have definitely lost communication, what is the exact mathematical probability that the battery failed?
And this isn't just an educated guess. It's rigorous math.
It's highly precise math. You look at your priors. A prior is your baseline belief before anything goes wrong. How often do these specific batteries fail? Maybe the manufacturer data says once every 10 years. Okay, how often do solar flares of that magnitude happen? Maybe meteorological data says once every 50 years.
So even though both of those things could cause the blackout, the battery failing is inherently more likely based on history.
Right, but you don't stop there. You look for more evidence in the network. Maybe you check the backup voltage sensor telemetry from 5 minutes ago. If the voltage was running extremely low 5 minutes before the blackout, the probability of it being a battery failure skyrockets from, say, 10% to 99%. You are constantly dynamically updating your beliefs based on every new piece of evidence.
But the book makes a really big point of mentioning that calculating this, doing this exact math, gets really hard really fast. They use the term NP hard.
Yes, that is a fundamental computer science term that basically translates to really, really catastrophically difficult to compute.
But why is it so hard? I mean, isn't it just adding and multiplying some percentages together?
It's the scale of the problem. If you only have 3 variables, battery, solar flare, voltage, it's trivial. A pocket calculator could do it. But imagine you are trying to predict the weather for a whole continent. You have humidity, temperature, wind speed, barometric pressure, ocean currents, urban heat islands, millions of variables. And they all interact with each other. A change in pressure changes the wind, which changes the temperature. Calculating the exact perfect probability involves summing up every single possible combination of every single variable. The math grows exponentially.
So it would take a modern supercomputer 1,000,000 years to give you the weather forecast for tomorrow.
Exactly. By the time it finishes the calculation, tomorrow is ancient history. So we have to cheat. Or, well, rather, we have to be incredibly clever with our algorithms.
The book details a few methods for this, starting with variable elimination.
Think of variable elimination like doing your high school algebra homework, but doing it highly efficiently. If you have a giant equation taking up a whole chalkboard, you could try to brute force solve it left to right. But a smart student steps back and sees that certain terms cancel each other out early on. Oh, I can solve for x over here first, and that completely removes half the equation. Variable elimination is the algorithm finding the absolute perfect order to do the math so it never does any unnecessary calculation.
But sometimes, even with that trick, the network is just too massive, and it's still too slow. And that brings us to something I found fascinating: Monte Carlo methods.
Right. When the algebra is simply too hard or too big to solve analytically, we simulate reality instead.
This is what I kept thinking of as the Doctor Strange approach, right? Viewing 14 million alternate futures to find the one that works.
In a very real way, yes. Instead of calculating the exact mathematical probability, you build a digital simulation of the satellite system. And then you just run that simulation 10,000 or 1,000,000 times. You literally roll digital dice for every single variable based on their probabilities.
So in some of these simulated universes, the battery fails. In some universes, the solar flare hits. In some, nothing goes wrong at all.
And then, after running 1,000,000 simulations, you just count the results. You say, okay, out of the 1,000,000 simulations, we lost communication in 10,000 of them. Out of those 10,000 blackouts, how many were caused by a dead battery? If the answer is 8,000, then you know your probability is roughly 80%.
You completely bypass the calculus and replace it with extremely fast counting.
Precisely. And this concept, simulation over calculation, is the absolute backbone of modern AI. When in doubt, simulate it a million times.
Okay, so we know how to calculate the odds of something happening. We have a solid grasp on probability. But knowing what might happen isn't the same thing as deciding what to actually do about it?
Correct. Knowing it might rain doesn't tell you whether to grab an umbrella or stay home. That brings us to utility theory.
This is where the algorithm actually asks, what do we actually want? What is the goal?
Exactly. In economics and in decision theory, we assign a concrete number to how desirable any specific outcome is. That number is called utility.
The book brings up the concept of the utility of wealth here, which is something I actually think about a lot in real life. If I take a $100 bill and I give it to a broke college student, they are thrilled. The utility of that money to them is massive. That's groceries for 2 weeks. It's a huge relief.
Right. It fundamentally changes their week.
But if I take that exact same $100 bill and hand it to a billionaire tech CEO, they probably won't even notice. It literally falls into the couch cushions of their yacht. The physical money is identical. It's $100. But the internal utility is vastly different.
That is the core economic concept of diminishing marginal utility. The graph curve eventually flattens out. The first slice of pizza you eat when you're starving is heaven. It's 10 out of 10 utility. The 10th slice of pizza just makes you feel sick. Negative utility.
And this is wildly crucial for programming algorithms, right?
Yeah.
Because an autonomous self-driving car needs to know that the utility of saving a pedestrian's life is infinitely higher than the utility of arriving at the coffee shop 1 minute earlier.
You absolutely have to encode those values mathematically. The car doesn't have a conscience. If you don't explicitly write down in the code that human life equals positive 1 billion points and being late equals negative 10 points, the car might make a terrifyingly optimal decision to run a red light just to save 30 seconds of driving time.
And this whole concept leads us to the golden rule of the entire book. If you are listening to this and you take only one single concept away from this entire deep dive, it should be this acronym, MU.
The maximum expected utility principle. It is the North Star of the field.
Break that down. What does that actually mean in plain English for the listener?
It means that a truly rational agent, whether that agent is a human being, a dog, or a billion-dollar robot, should always, without exception, pick the action that maximizes the statistically weighted average of its future happiness or its future utility.
Walk me through the actual math of that in a simple scenario.
Okay, let's look at a financial action. Say your action is invest $10,000 in tech stock A. Now, based on your models, there is a 50% chance the stock skyrockets, which gives you a utility of positive 100. But there's a 50% chance a company goes bankrupt, giving you a utility of negative 50. You do the weighted math. 50% times 100 is 50. 50% times negative 50 is negative 25. Add them up. 50 minus 25 equals 25.
So the expected utility of that investment is exactly 25 points.
Right. And then you compare that number to your other option. Let's say your other action is keep the money hidden under my mattress. There is a 100% chance the money just stays exactly the same. The utility is 0. It doesn't gain, it doesn't lose.
And since 25 is mathematically greater than 0, the algorithm says invest.
Exactly. Rationality in this mathematical framework isn't just ignoring risks or playing it incredibly safe. It's weighing the risks precisely. Even if there's a massive risk of loss, if the potential gain is high enough to offset it in the weighted average, the mathematically rational move is to take the leap.
Okay, that makes perfect sense. So that wraps up part 1. We know the exact odds of the world. We know exactly what we want to achieve. But that framework is really just for a single, isolated decision. And real life isn't a single decision. It's a relentless stream of one thing after another.
Correct. We are now zooming out. We are moving from a single photograph to a feature-length movie. This brings us to part 2 of the book, sequential problems.
And the absolute star of this section is the MDP, the Markov decision process.
The MDP is the industry-standard mathematical model for sequential, multi-step decision-making. It has 4 core components. States, which is where you are right now. Actions, which are the things you can do. Transitions, which are the rules for how the world changes when you act. And rewards, the point system, or utility, you get along the way.
But why is it called Markov? Who exactly is Markov?
Andrei Markov was a brilliant Russian mathematician from the early 20th century, and the Markov assumption, which is named after him, is a crucial simplifying rule that literally saves our computers from melting down due to computational explosion.
What is the actual rule?
The assumption states, the future depends only on where you are right now and not on the history of how you got here.
Wait, really? Isn't that just a massive lie? In human life, history almost always matters.
It is definitely a bit of a lie, yes. But it's a highly necessary, pragmatic lie. Think about an autonomous car pulling up to a busy intersection. Does it fundamentally matter to the car's next decision if it arrived at that red light by speeding down the highway, or by driving slowly through a neighborhood, or if it had just spent 20 minutes doing donuts in an empty parking lot?
I guess not. All that really matters for the very next action is, I am currently at an intersection, the light is currently red, and there is a pedestrian currently in the crosswalk.
Exactly. The current state encapsulates absolutely everything you need to know to make a safe decision in that specific millisecond. If the computer had to actively remember and process the entire history of its 3-hour drive just to decide whether to turn left or right, it would run out of RAM instantly. The Markov assumption lets us cut the cord to the past.
To see this concept really put into action, the source material does a massive deep dive into a system called ACSX. And this isn't just theory. This is the actual collision avoidance system used in modern aviation around the world.
This is an incredibly high-stakes application of MDPs. We are literally talking about algorithms preventing massive metal tubes full of people from crashing into each other at 500 miles an hour.
So imagine the terrifying scenario.
Yeah.
You are the digital autopilot on a Boeing.
Yeah.
You have radar and transponder sensors screaming at you that another plane is approaching rapidly on a crossing flight path. You have a split second to decide. Do I tell my human pilot to climb immediately? Do I tell them to dive? Do I say stay exactly level?
And here's where the trade-off becomes agonizing. Why is this hard? Why wouldn't this system just yell, climb? The absolute millisecond it sees a blip on the radar 30 miles away.
Well, safety first, right? Better safe than sorry.
But think about the human pilot in the cockpit. If the computer system flashes red and yells, climb, every single time another plane is 20 miles away, which happens constantly in crowded airspace, what does the pilot eventually do?
It's the classic boy who cried wolf. The pilot gets annoyed by the constant false alarms. They start silencing the alarm, or they start second-guessing the system.
Exactly. Or, worse, they make a sudden, violent maneuver that spills coffee everywhere and injures flight attendants, all for a plane that was never actually going to hit them. So the utility function programmed into ASEX has to balance two fiercely opposing forces. Goal one is safety. Avoid a mid-air collision at all costs. Give the system a massive penalty, like -1 billion points for a crash state.
Okay, that's obvious.
But goal two is efficiency, or what they call minimizing alerting cost. You give the system a small, constant penalty for issuing any alert at all. You train the algorithm to only bother the pilot if it is mathematically absolutely necessary.
So the algorithm is essentially constantly fighting itself in real time.
In a way, yes, it's constantly calculating. Is the mathematical risk of a crash high enough right in this exact second to justify the point penalty of annoying the human pilot?
So how do we actually solve this? How does the computer look at all these moving planes and find the perfect, flawless strategy? The book talks about generating value functions.
Think of a value function in this context like a giant, invisible 3D heat map drawn across the sky.
A heat map. Okay, paint that picture for me.
So the specific coordinate state where two planes actually intersect and crash, that central point is red hot, maximum danger, negative infinity points.
Right.
Now imagine the airspace state just 1 second before the crash. That state is also glowing red hot because at 500 miles an hour, 1 second out, it's practically impossible for a human to pull up in time. You are essentially already dead.
Okay, and what about a state, say, 1 minute before the theoretical crash point?
That zone is maybe orange or yellow. It's a dangerous trajectory, yes, but you still have plenty of time and distance to execute a gentle turn.
So this mathematical heat map basically ripples and spreads outward from the central point of disaster.
Exactly. That algorithm is called value iteration. You start at the end goal, in this case, the crash, and you mathematically ripple the badness values backwards through time and space. Eventually, the computer generates a complete map of the entire sky. If the plane is flying through a green zone, the system stays quiet. If the trajectories drift into an orange zone, the system wakes up and prepares. If it ever crosses into a red zone, it immediately screams, climb.
That is deeply fascinating. It's essentially predicting the future by working systematically backward from the worst-case scenario.
Ideally, yes, that's how we want it to work. But there is a massive catch. For incredibly complex environments like the game of chess or Go or managing a power grid, the map is just too big to draw beforehand. You physically cannot pre-calculate a heat map of every single possible chessboard configuration. There are more potential moves in a game of chess than there are atoms in the observable universe.
Right, the book calls that the curse of dimensionality. The math just blows up.
So we can't pre-plan. Instead, we use something called online planning. And the source material heavily highlights a technique called Monte Carlo tree search, or MCTS. Just for context, this is the exact algorithm that the famous AlphaGo AI used to defeat the human world champion in the game of Go.
Really? How does that work if it can't memorize the board?
It doesn't try to plan the whole game, it only plans right now.
Yeah.
It sits in the current, immediate state of the board and essentially says, I have no idea what the perfect overall strategy is, but let me just rapidly simulate 10,000 completely random, fast-forward games, starting from this exact position.
So it's playing out 10,000 imaginary games in its head in a fraction of a second.
Yes. It tries a move. Okay, if I move my knight here, and then we both just play completely random moves until the end, I win 60% of those simulations. But if I move my rook instead, I only win 40% of the simulations. Therefore, without knowing the grand strategy, I just move the knight.
It relies on rapid, massive simulation rather than trying to store a giant, impossible map of the universe.
Exactly. It uses sheer computational speed to peer just far enough into the future to make the next move.
Okay, so that completely wraps up MDPs.
Right.
We have a clear model of the physics of the world, and we know how to plan paths through it. But now we are entering the real danger zone. This is part 3 of the book, Model Uncertainty.
This is where the field gets really, really interesting. This is the realm of reinforcement learning.
The massive twist here is that we don't have the rule book anymore. We don't know the probabilities of the world. We don't know where the rewards are hidden. The agent is basically just dropped into the maze with amnesia.
Exactly. You just have to act, watch how the world reacts, and figure out the rules of physics and the reward system as you go. You are literally learning entirely from raw experience.
And this inevitably brings us to the classic philosophical and mathematical dilemma: exploration versus exploitation.
Also known as the multi-armed bandit problem.
Let's really paint this picture for the listener, because it's such a perfect metaphor. Imagine you walk into a flashy casino in Las Vegas.
You are standing alone in front of a long row of slot machines, what they used to call the one-armed bandits, and you have a bucket of tokens in your hand.
Okay, so I take a token, I put it in machine A, I pull the lever, the wheels spin, and nothing. I lose. I take another token and put it in machine B, I pull the lever, cling, cling, cling. Lights flash. I win $5.
Oh, nice. You have data now.
Now, here is the core dilemma of the whole field.
Yeah.
Do you take your very next token and put it back into machine B?
Well, yeah. Logically, it just paid out. It's a winner. That is called exploitation. You are using the limited knowledge you already have to guarantee a known reward. You know B works, so you milk it. But what if machine C, which is sitting right next to it and which you haven't even touched yet, is secretly rigged to pay out $1 million on the first pull?
But if I try machine C, I might just lose my token and get nothing.
That is called exploration. You purposefully sacrifice short-term, guaranteed certainty for the potential of long-term, massive knowledge. And it's a brutal trade-off. If your algorithm only ever exploits, it gets stuck in a local minimum. It just keeps winning $5 forever while $1 million sits right next to it. But if your algorithm only ever explores, it just endlessly tests broken machines until it completely goes broke.
So how do the world's best algorithms actually solve this? The book mentions a strategy called epsilon greedy.
It's a very simple but incredibly elegant and robust strategy. You basically just flip a weighted digital coin before every single move. Let's say you set your epsilon value to 10%. That means exactly 90% of the time, the algorithm acts greedily. It just exploits machine B because the data says it's the best one found so far.
And the other 10% of the time?
The other 10% of the time, the algorithm forces itself to go completely wild. It pulls a totally random lever. It tries a completely new path. This built-in randomness mathematically ensures that the agent never gets permanently stuck in a rut. It continuously scans the unknown horizon just in case there is something vastly better out there.
There's another exploration strategy the book mentions that I want to touch on. It's called RMAX. I love this one because it honestly sounds like a cheesy motivational poster you'd see in a corporate office.
It really does. It is formally known as the principle of optimism in the face of uncertainty.
Basically, the rule is, If the agent hasn't explored a specific part of the map yet, it is programmed to automatically assume that unknown part of the map is the most awesome place in the universe.
Exactly. RMAX literally writes into its internal code. I have absolutely no idea what is behind door number 3, so I'm going mathematically assume there's a massive pile of gold behind it.
So the algorithm immediately rushes over there to check it out. It's intrinsically motivated by curiosity.
Right. And if it kicks open the door and it turns out to just be an empty broom closet, it says, oh, bummer. It updates its internal map with the new negative data and it immediately moves on. But that initial forced extreme optimism drives highly efficient exploration. It treats total ignorance not as a risk, but as maximum potential.
I feel like there is a profound life lesson hidden in that math.
There definitely is. Assume the unknown is great until proven otherwise.
Now, let's talk about the heavy hitters.
Yeah.
Q learning. The book calls this model-free learning.
Yes, this is a massive shift. Model-free learning is much more akin to building human muscle memory. You aren't actively trying to learn how the deep physics of the world works. You aren't drawing a map of gravity. You are simply learning, when I am in situation X, doing action Y mathematically feels good.
So you don't have a map. You just carry around a giant cheat sheet, which is the Q table.
Right. It's literally just a spreadsheet of states and actions. Every single time the robot touches a hot stove, it writes down in the spreadsheet, stove state plus touch action equals massive pain. Every time it eats a cookie, it writes, cookie state plus eat action equals good. After a million tries, you have a perfect instruction manual for life.
But wait, what if the environment is just too complex for a simple spreadsheet? Like, say, an agent trying to beat the classic video game breakout, or a Tesla trying to navigate a real city. You can't possibly list every single pixel combination or every single leaf blowing across the street in a table. The table would be larger than the hard drive.
That's exactly where the concept of generalization comes in. Instead of using a flat spreadsheet, we swap it out and use a deep neural network to guess the values. This combination is what we call deep Q learning. It's what ignited the modern AI boom.
The source material uses the classic mountain car example here to explain this. I really want to visualize this for the listener because it perfectly explains why reinforcement learning is so much smarter than just, following your nose toward a goal.
Sure, it's a great thought experiment. Imagine a steep U-shaped valley. At the very bottom of the valley, sitting still, is a little yellow car. At the top of the steep hill on the right side, there's a flag. That flag is the goal.
Okay, so the car obviously wants to go right.
But here's the catch. The car has a terrible, incredibly weak engine. If the algorithm just pushes the gas pedal and drives right, it creeps up the hill a few feet, gravity eventually overpowers the engine, and it just sadly slides back down to the bottom. It's completely stuck.
A simple, greedy algorithm would just keep mashing the gas pedal to the right forever, wouldn't it? Because mathematically, moving right decreases the distance to the goal.
Exactly. A greedy algorithm would just violently bang its head against the side of the hill until the end of time. It would never reach the flag.
So how does a reinforcement learning agent actually solve it?
Through that forced exploration we talked about earlier. By making random moves, it eventually, purely by accident, tries driving away from the goal. It drives left.
It goes the wrong way.
Yes. It drives up the left side of the valley, it gains altitude, then it throws it in reverse and swings back down. It converts that potential energy into kinetic energy. It gains massive momentum. Now it has enough raw speed to zoom all the way across the valley, up the right hill, and reach the flag.
It literally learned that it had to take one massive step backward in order to take 2 steps forward.
Exactly. Over thousands of runs, the neural network learns that the invisible value of being high up on the opposite hill is extremely high. Not because the flag is there, but because it's the necessary launch pad to get to the flag. The algorithm fundamentally understands the long game.
That is just brilliant. Now, briefly, before we jump to the next section, the book brings up a very practical problem. Sometimes you simply cannot learn by trial and error. You cannot train a billion-dollar autonomous helicopter by letting it crash into the ground 10,000 times until it figures out how the rotor works.
No, absolutely not. That would be financially ruinous and completely unsafe.
So the researchers use imitation learning. We basically just force the algorithm to sit there and watch a human expert fly the helicopter. But the book introduces this concept called inverse reinforcement learning, or IRL. And this felt exactly like a detective story to me.
It really is algorithmic detective work. Standard RL says, here is your point system. Now go blindly find the behavior that gets the most points. Inverse RL completely flips the script. It says, Here is hours of video of a master human expert doing the behavior perfectly. I need you, the algorithm, to deduce what internal point system they were trying to maximize.
So an autonomous car watches a human driver approach a yellow light and hit the brakes.
And the computer sits there and thinks, why did the human do that? Stopping physically slows them down, which contradicts the goal of reaching the destination quickly. Therefore, the human must have a massive hidden negative point penalty for crashing their car or breaking traffic laws.
It infers the underlying motivation from the action.
Right. It learns the actual spirit of the law, not just the rigid letter of the law. It's trying to reverse engineer human desires.
Okay, we are making great time here. We've successfully handled bad physical odds, we've handled sequences of time, we've handled completely unknown environments. Now, the book decides to just make everything terrifyingly harder.
Part 4. State uncertainty. The true fog of war.
This is the mind-bending domain of the POMDP, the partially observable Markov decision process.
In all the previous sections, even when things were tough, the car at least knew it was at the bottom of the hill. The airplane at least knew its exact GPS coordinates. Now, our sensors are broken, we might be sitting in state A, but our sensors are glitching and telling us we might be in state B.
Right, so we have to force the algorithm to stop thinking in absolutes. It can no longer say, I am at coordinate X. We introduce the concept of belief states. The computer starts thinking, based on my noisy radar, I am 60% sure I am currently in the hallway and 40% sure I am actually still in the kitchen. The state itself is no longer a physical place. The state is a floating probability distribution inside the computer's own memory.
The classic famous example the book uses here, and it's so relatable, is the crying baby problem. It's a foundational example in the literature for a very good reason. It perfectly captures the agony of state uncertainty.
So imagine you're a new parent. You are asleep. Suddenly you hear the baby start crying from the nursery. That sound is your observation. But you do not know the actual hidden state of the baby. Is the baby crying because it is hungry? Or is the baby crying because it is just cranky and tired?
Right, you physically cannot look inside the baby's stomach to check the fuel gauge. You have absolute state uncertainty.
And as the parent, the agent, your available actions are feed the baby or ignore the baby and try to sleep.
Now look at the utility outcomes. If you choose to feed a baby that is actually hungry, you get a huge reward. The baby eats, goes to sleep, there is silence, you have happiness. But if you choose to feed a cranky baby who isn't hungry at all, well, you just wasted an expensive bottle of formula, you wasted 20 minutes, and the baby is probably still crying because it really just wanted to be rocked.
And what if you choose to ignore a baby that is legitimately hungry?
Complete disaster. Massive negative utility. The baby just screams louder and louder. Nobody gets any sleep. Total system failure.
So the belief state is your internal running calculation of the odds. You wake up and think, okay, I haven't fed him in exactly 4 hours, and he is screaming. My internal belief probability that his hidden state is hungry just shot up to 90%.
Exactly. And you base your action on that 90% confidence. You don't know for an absolute fact, but the statistical odds dictate that feeding is the optimal mathematical choice.
To keep track of all these shifting beliefs, especially for a robot physically moving around a map, the book introduces the concept of filters.
Yes, state estimation filters, things like the Kalman filter, which assumes everything moves in smooth bell curves, which is great for tracking airplanes.
But I want to focus on the particle filter because the visual metaphor the book provides is just amazing. They use the example of Spelunker Joe.
Spelunker Joe, I love that section. Imagine poor Joe. He is a cave explorer, and he is deeply lost in a massive, completely pitch-black cave system. He has a paper map of the cave in his pocket, so he knows the overall shape of the tunnels, but he has absolutely no idea where he currently is on that map.
So how does he figure it out using a particle filter algorithm?
Imagine Joe has a magical, infinite bag of glowing dust. He takes thousands of little specks of dust. Let's call them ghost Joes. He sprinkles them evenly all over his paper map. Every single square inch of the cave map has a tiny ghost Joe standing on it.
So his belief is completely spread out.
Yeah.
He is essentially simulating that he could be literally anywhere.
Right. Uniform distribution. Now, real Joe in the dark takes one single step north.
Okay, he steps north.
On the computer map, we instantly simulate that exact action. We forcefully move every single one of those thousands of ghost Joes one step north.
Okay, so the entire cloud of glowing dust shifts north on the paper.
Now, in the real world, real Joe steps north and immediately smacks his face into a solid rock wall. Ouch.
He receives a definitive observation. There is a wall directly north of me.
Now, the algorithm filters the dust. We look at the map. Any digital ghost share that moved north and did not hit a simulated wall on the map, we delete them. We kill the ghosts.
Wait, really? You just wipe them out?
Yes, because if that specific ghost Joe was, say, standing in the middle of a massive open cavern and moved north, he wouldn't have hit anything. But the real Joe did hit something. Therefore, the real Joe physically cannot be in the middle of that cavern. The simulation contradicts reality.
So you instantly wipe out thousands of possibilities that contradict the hard evidence.
Exactly. And the ghost Joes that did hit a wall in the simulation, we keep them. In fact, we clone them. We multiply them to represent our increased confidence in those locations.
So after just a few cautious steps in the dark, move north, hit wall, turn west, move forward, feel open space, turn south, you are constantly, ruthlessly killing off the ghost particles that guess wrong.
And very, very quickly, the only ghost Joes left alive on the map are all clumped closely together in the exact specific corner of the cave where real Joe is actually standing. The algorithm has successfully distilled absolute certainty out of pure randomness.
It's essentially playing a massive game of Guess Who, but played with physics and probability.
It is. It's a brilliant workaround. But, as the book points out, computationally, trying to plan a path through this shifting belief space is incredibly hard. The authors mention that mathematically it is PS-space complete.
Which, if I remember my computer science classes, implies it's significantly harder than NP hard.
Yes, by orders of magnitude. It's vastly more complex than standard MDPs because the state you are tracking isn't a single dot on a grid anymore. It's a continuous flowing probability distribution. You are trying to plan a solid path across a constantly shifting landscape of liquid beliefs.
So to handle that, the researchers use mathematical tricks like alpha vectors to approximate the shapes. And conditional plans basically writing huge branching FN trees like, if I hear a baby cry, I execute plan X. If I don't, I default to plan Y.
Right. Because calculating the perfect answer takes until the end of time, we usually have to settle for very smart, calculated approximations. Perfect is the enemy of good in POMDPs.
You might take a breath. We are firmly in the home stretch now. We have completely dealt with the internal fog of broken sensors. Now we have to deal with the ultimate external chaos. Part 5 of the book, multi-agent systems.
The final complexity, other sentient people.
Until this exact chapter, the environment was just nature. Rocks, gravity, sand, caves. The environment is stochastic, sure, but it doesn't have desires. It doesn't care about the robot.
Yeah.
But now we are adding other intelligent agents into the simulation. And they have their own utility functions. They want things.
And they want things that might directly conflict with what you want. Welcome to game theory.
We start with the absolute basics, simple games, like rock, paper, scissors.
The quintessential game. Now, mathematically, there is no single dominant optimal move in rock, paper, scissors. If I sit here and tell you I ran the supercomputer and rock is objectively the best move, you will just adapt, play paper every time, and crush me. My best move depends entirely, 100%, on your move.
So instead of an optimal move, we look for a state of balance, the Nash equilibrium.
Named after John Nash. A Nash equilibrium is a mathematical stalemate. It's a very specific situation where neither of us can improve our score by changing our strategy, assuming the other person doesn't change theirs. In rock, paper, scissors, the equilibrium is actually to play completely, truly randomly. Exactly, 1/3 rock, 1/3 paper, 1/3 scissors. If I strictly adhere to that mathematical randomness, you cannot possibly beat me on average, no matter what genius strategy you invent.
But the real world isn't just math. Humans aren't always rational. And this leads to my absolute favorite part of the book, the traveler's dilemma. This thought experiment completely blew my mind when I read it.
It's a fascinating, deeply troubling paradox. It really highlights the fragile cracks in pure, unadulterated mathematical rationality.
Okay, listeners, seriously, imagine this scenario. You and I fly to a beautiful tropical island for vacation, but disaster strikes. The airline completely loses both of our checked bags.
Tragic. Vacation ruined.
Completely. Now, we both had identical brand new suitcases, and we both had identical rare antiques packed inside. The airline manager is very apologetic. He offers to reimburse us, but he separates us into 2 different interrogation rooms.
The classic prisoner setup.
Right. The manager says, I don't know how much the antiques were worth. I want you each to write down the value of the suitcase on a piece of paper, anywhere between $2 and $100.
And we do this totally secretly. I can't look at your paper.
Secretly. Now here's the massive catch. The manager says, if you both write down the exact same number, I will assume you are telling the truth, and I will pay you both exactly that amount. But
If I get two different numbers, I will assume the person who wrote the lower number is being painfully honest, and the person who wrote the higher number is being a greedy liar.
So what happens to the payout?
Manager says, I will pay both of you the lower number. However, to reward the honest person, I will give them a $2 bonus, and to punish the liar, I will deduct $2 from their payout.
Okay, so let's actually game this out step by step. We are sitting in separate rooms. We both logically want the maximum amount of money. So the obvious first thought is we both just write down $100.
Yeah. If we both write $100, they match. We both get handed a crisp $100 bill. That's a great, easy payday.
I'm sitting alone in my room staring at the paper thinking, I know he wants $100. If he writes $100 and I write $99, the manager thinks I'm the honest one. I get the lower number, $99 plus the $2 honesty bonus. That's $101 for me, and he gets punished, so he only gets $97. So just by undercutting me by a single dollar, you instantly make more money than the maximum. You have a massive mathematical incentive to undercut me.
Yes. My greed tells me I want that extra dollar, so I cross out 100 and I switch my answer to $99.
But wait, I'm sitting in my room, and I'm a smart, rational agent too. I know you understand the rules. I know you're going to be tempted to undercut me to get $101. So I think he's definitely going to write $99. But if I write $98, I'm now the lower number. I get $98 plus the $2 bonus. That's $100 for me. And he gets screwed and only gets $96.
But I anticipate that you are going to anticipate my undercut. So I think he's going to $98, so I need to switch to $97.
And I realize that, so I switched to $96.
And I go to $95. And logically, mathematically, if you follow this strict Nash equilibrium logic all the way down the rabbit hole, where does the elevator finally stop?
It stops at the absolute bottom. We both write $2.
Exactly. The only purely rational, mathematically stable point in the entire game is for both of us to rate the absolute minimum amount, $2. Because at $2, you physically cannot undercut me anymore to get a bonus.
Which is completely, utterly insane. We could have just written 100 and had $100, but logic forced us into poverty.
And here's the punchline. When economists actually play this game in a lab with real living human beings, the humans almost always ignore the math and just pick numbers in the $97 to $100 range.
Because humans trust each other just enough.
Yes. The humans are technically mathematically irrational, but because they are irrational together, they walk away with way more actual cash than the perfectly rational AI agents do.
That is such a profound, deep point about how AI might struggle to interact with us in the real world. Hold on to that thought for the outro because I want to come back to it. But first, we have to quickly scale this up. The book introduces Markov games.
Right. This is essentially taking rock, paper, scissors and playing it while running around on a grid. Imagine a bunch of warehouse robots moving boxes. If I decide to move into a narrow hallway, I physically block you from using it. My chosen action instantly degrades your available state.
It becomes a highly complex, aggressive dance.
It really does. And to survive, the agents use predictive techniques like fictitious play.
Fictitious play? What exactly is that?
It's a psychological trick. It's where my algorithm pretends, just for a moment, that your algorithm has a fixed, unchanging strategy. I sit back, I observe you, and I learn exactly how to counter and beat your current style. Then, of course, your algorithm realizes I'm beating it, so it instantly pivots to a new strategy. Then I observe the new strategy, update my internal model of you, and adapt again. We cycle through hundreds of strategies, constantly dancing and adapting to each other's shadows.
It's like a high-speed game of chess where the rules keep changing. And finally, the absolute peak of complexity in the book. What if we aren't fighting? What if we are actually on the exact same team? Collaborative agents.
Ah, yes. Deep POMDPs. Decentralized, partially observable Markov decision processes. Unquestionably the hardest acronym of the day.
I stumbled over that one a few times reading it. The core scenario here is a team. Let's say a team of 5 Mars rovers. They're all working together to map a crater, but they cannot talk to each other constantly. The satellite bandwidth is just too low or too expensive.
So I have to guess what you are doing based on limited data, and you have to guess what I'm doing so we don't accidentally crash into each other or waste time scanning the exact same rock twice.
The book uses this incredible simulation called the predator-prey hex world. Imagine a team of 4 robotic predators, like a pack of wolves, trying to catch a fast, erratic prey like a rabbit on a hexagonal grid map. To win, they have to surround it completely.
But if they don't perfectly coordinate, if wolf number 1 steps left to block an exit when he absolutely should have stepped right, The rabbit finds the tiny gap and slips through.
But the wolves can't just pull out a radio and shout, "Hey, everybody go left!" to coordinate.
Right. They are decentralized, so they have to use incredibly complex tools like coordination graphs, which mathematically map out exactly who needs to talk to whom, and algorithms like JSP.
JSP. Joint Equilibrium-Based Search for Policies. How does JSP solve a team problem?
Think of it exactly like a professional jazz band trying to improvise a new song. You can't all play random notes at once.
Yeah.
So the algorithm fixes everyone else's behavior first. It says, okay, we are going to assume the drummer is going to play this exact simple beat. Then the algorithm mathematically optimizes the bass player to play perfectly in sync with that specific drum beat.
Okay, so the bass and drums are locked in.
Then it fixes the bass player's new routine, and it optimizes the piano player to match the bass. It rotates through the entire team, freezing everyone except one agent, optimizing that one agent, and then moving to the next. It cycles over and over until the entire group clicks into a beautiful collaborative harmony.
Wow. That is a lot of extremely heavy algorithms.
Yeah.
We have officially unpacked the entire core framework of the book.
We really have. We covered a massive amount of ground.
Let's synthesize this whole journey for the listener before we wrap up. We started with a simple probability, just trying to mathematically represent an uncertain world. Then we added the dimension of time with MDPs. Then we stripped away the rulebook and forced the agent to learn via reinforcement learning. Then we smashed the sensors and added the fog of TOMDPs. And finally, we threw in other minds with game theory.
What you just described is literally the foundational blueprint for modern autonomy.
So what? I mean, why should the average listener care about this massive alphabet soup of acronyms? MDPs, POMDPs, JESP.
Because this math isn't just about imaginary robots on a hex grid anymore. It's about us. It is deeply embedded in the systems that are actively running our world right now.
How so? Give me real-world impact.
Look closely at self-driving cars. Waymo, Tesla. That entire industry is essentially just solving a massive POMDP. The car is constantly dealing with horrible sensor noise from rain, it is predicting the irrational behavior of pedestrians, and it is trying to maximize a utility function of safety and speed. It is running these exact mathematical equations thousands of times a second just to keep you alive on your commute.
Okay, that's huge.
Or look at ChatGPT or any of the massive modern language models. How do you think they get so incredibly good at sounding human? A process called RLHF, reinforcement learning from human feedback. That entire training process is a direct descendant of the imitation learning and inverse RL we just discussed. We, the humans, are the experts. We're actively teaching the AI our complex hidden utility function by clicking the thumbs up or thumbs down buttons on its responses.
So this book really is exposing the actual engine block under the hood of the current AI revolution.
It absolutely is. But more than the tech, I honestly think it's a mirror for human thought. Once you learn these concepts, you see them everywhere. We naturally do approximate inference in our heads when we hear a rumor. We constantly battle exploration versus exploitation when we try to decide whether to go to our favorite restaurant or try the new place down the street. We use mental particle filters when we get turned around in a new city.
We are just running these exact same algorithms on biological wetware instead of silicon chips.
Precisely. It's the math of life.
I want to leave the listener with that one provocative thought we touched on earlier from the traveler's dilemma. The pure, flawless math dictates that the rational move is to bid $2 and screw the other guy. But human beings naturally bid $100 and cooperate.
Right. It strongly implies that hyper-rationality, in a strictly selfish mathematical sense, can actually be highly suboptimal in the messy real world. Being perfectly selfish makes everyone poorer.
So as we march toward the future, and we build these increasingly powerful AI agents using these exact equations to be perfectly mathematically rational, will they actually be able to work alongside us?
That is the big existential question of AI alignment right now. Because if an advanced AI plays a real-world traveler's dilemma with you, and its core programming forces it to bid $2 because the math proves it's the right move, and you bid $100 expecting human trust, you get penalized. The AI exploits you. The partnership fundamentally fails.
So maybe, just maybe, the final frontier of this research is that we actually need to figure out how to mathematically program a little bit of irrationality, or maybe we call it cooperative human grace, into these systems to make them genuinely good partners.
I think we absolutely might have to. We need them to understand that sometimes maximizing long-term utility means taking a leap and trusting the other guy, even if the cold equations tell you not to.
That is a brilliant place to leave it. On that note, next time you are standing in the grocery aisle, paralyzed by pasta sauce,
Yeah.
or deciding whether to buy that expensive coffee or save the $5, ask yourself, what is my actual utility function today? And am I exploiting my comfort zone, or am I exploring the unknown?
Always be exploring.
Thanks for joining us for this deep dive. We'll see you all next time.